Okay, so I've got this ball, this 3-pound ball, traveling at this rod at 6 feet per second. Smashes that 5-pound rod, which was initially at rest. I want to figure out what the angular velocity of the bar is right after impact, knowing that the coefficient of restitution is 0.8. So at this point, I'm going to use that coefficient of restitution. Of course, I need to use that at the point of impact. Okay, so let's go ahead and again, what I've got here is E equals VB2 minus VG2 divided by VG1 minus VB1. So again, E is 0.8. Okay, VB2, that is the velocity of 2. Now again, I'm trying to find the angular velocity about 0.0. So that angular velocity, that the velocity of the endpoint is 2 feet times that angular velocity that I'm trying to find, right? Because it's 2 feet away from 0.0. So it's pure rotation about 0.0. So that velocity there at the point of impact is 2 omega. Okay? Minus VG2, which again, I don't know what it is. We'll figure it out. And that's all going to be divided by the initial of the ball is 6. The initial of point B at the end there is 0. Right? So here's an equation that'll help me find the rotation after impact. But I've also have the velocity of the ball after impact. So I need another equation. That equation is going to be that the angular velocity is conserved around 0.0 because for the total system, because I'll take the entire guy here. Okay, and figure out with that impulse then being internal to the system, there is an impulse at O, but if I take the angular momentum of about 0.0, then it disappears. Okay, so initially the only thing that's happening is the ball, so that's RMV at this point. We're going to treat it like a point mass. We'll say that's going in the negative z direction. Okay, if z is going up, it's going to be going clockwise. So it's going to be negative r of 2, m of 3 divided by 32.2 times 6, which is the velocity it's coming in at. Afterwards, it's also going to have an RMV. We'll assume it keeps going in the same direction, probably just slows down a little bit. So it's going to be 2 times 3 divided by 32.2 times the velocity of the ball afterwards. That rod is also probably going to be going negative. We'll put that negative. It's going to get hit. I see no reason it's going to go the other direction, right? So it'll be negative as well. The moment of inertia about the rod is 1/12 ml squared, where m is, on this guy, 5 pounds divided by 32.2. L is 4 squared, and then that's times omega. So now I've got 2 equations and 2 unknowns, right? I've got coefficient of restitution equation. I've got conservation of angular momentum about 0.0 for the entire system. I can find that omega then, solving these equations, omega is 3.47 radians per second. And for the record, VG2 then becomes 2.14, which is less than the 6 feet per second it started with, which makes sense. Okay, it keeps going in the same direction though. Okay, so again, angular momentum is conserved about 0.0, coefficient of restitution at the point of impact, which is actually at point B, as well as the ball.